Welcome to the 45th lecture of this course, and I'll discuss a last problem based on half-wave rectifier for the time being. It's a problem. Look at the statement of the problem. A half-wave rectifier is used to supply 12 volt DC to a resistive load of 500 ohm. If the diode used has a forward resistance of 25 ohm, determine the value of AC voltage supplied to the circuit. So it is a half-wave rectifier. First of all, a half-wave rectifier. So I draw the circuit for this half-wave rectifier. Look at the solution. Initially I draw the half-wave rectifier. A half-wave rectifier, you have a diode here and followed by a load resistance, and an AC is applied here. At this point you have some AC, which is the secondary output, you can say output. I'm not showing the transformer here because transformer specifications are not given. This is the load resistance RL and this is the diode D having some forward resistance RF. Now, as per the problem, a half-wave rectifier is used to supply 12 volt DC. That is the voltage which I obtain here at the output of this rectifier or across this load is 12 volt. That is the average value of average DC value which I obtain here is 12 volt. It is 12 volt which I am obtaining at this point here. I'll obtain at this point 12 volt DC. Of course, the nature will be like this. Suppose I say this is the output voltage, and of course the DC value of this is 12 volt, or the average value of this rectified output is this much, 12 volt DC with a resistive load of 500 ohm. Means the value of this RL, what is given to you, that this RL value of this load, resistive load, this given RL is 500 ohm. If the diode used has a forward resistance of 25 ohm, that is this RF, it is given that this RF, I'll say here that this RF is 25 ohm, and of course this VDC is 12 volt of the rectified output. Determine the value of AC voltage supplied at this point. That is, what is the value of this VI? It is asked to find the value of this VI at this stage here, and these three parameters are given to it. It's a reverse problem actually. If you see that, what is this input voltage VI here, or what is the RMS value of this? Generally this AC voltage, of course it's a AC here. AC voltage is expressed in terms of your RMS value. So I have to find the value of this input voltage that must be applied here in order to obtain a DC voltage of 12 volt under these circumstances, if there is a load resistance of 500 ohm and of course this diode is having some forward resistance of 25 ohm. So very first thing, I know that VDC, look at the solution. I know since VDC is equal to IDC into RL, IDC into RL. This is the current flowing here will be IDC. Average value of this will be IDC. So can I say VDC? If I apply a voltmeter between these 2 points, if I apply simply a voltmeter here, suppose I say it's a voltmeter. This voltmeter will give me the value of the DC current and this load resistance RL here. If I apply a voltmeter between these 2 points, which is providing me 12 volt IDC into RL, this implies that I can say that the value of IDC will be VDC upon RL. This VDC is given to you 12, RL is 500 ohm, and if I calculate this, I have done the calculation. This implies that the value of IDC which I obtained from here is 0.024 ampere. I want to cross check it. You to cross check it. It is 0.024 ampere, or I can say it is 24 milliampere. One is the same thing. Now I have obtained this IDC. Now it's a half-wave rectifier, and I know that the IDC, the average value or the DC value for a half wave rectifier or the current the DC current or the average current of this output is given by Im by pi. It is given by Im by pi. So from here I can say that this Im is equal to pi into IDC. I just cross multiply this, pi into IDC. And now since this Im, already I have done this many times with you, that this since Im, this maximum current will occur when this Vi is maximum, so it is equal to Vm upon Rf plus RL upon Rf plus RL. So I can say that this, I substitute this value as Vm upon Rf plus RL. So Vm upon Rf plus RL. Which Vm I am talking about? I am talking about the maximum value of the signal which is applied here at this point. The signal which is applied here at this point. I am talking about this Vm. This Vm. When this is maximum, of course here you let this current will be Im. Im is equal to Vm upon Rf plus RL. So Vm upon Rf plus RL, Im is equal to this much, is equal to pi into IDC. So from here I can find the value of Vm. I can find the value of the maximum amplitude of the input signal which I apply here. The maximum value of this will be equal to, this implies that the value of Vm will be pi into IDC into Rf plus RL. Rf plus RL. Of course, I know the value of IDC. I have calculated this. I substitute this value as 0.024. Substitute this Rf is equal to 25 ohm, which is given to you. And this RL, substitute this is equal to 500. Value of pi, everyone knows it, 3.14. Or you can do it directly from a calculator. From here, if I find the value of Vm, this implies that value of Vm, which you will obtain from here, as per my calculation, it is 39.58 volt. This is the value of Vm. But whenever it is asked to determine the value of AC voltage supplied, so whenever AC is asked, it is in terms of RMS. So from here, therefore I can say that VRMS. VRMS means RMS value of this signal, not of this signal. RMS value of this is Im by pi or Vm by pi. But the RMS value of an AC signal is equal to Vm upon root 2. Remember that. It is Vm upon root 2. So from here I can say that the signal which is applied here, VRMS, is Vm upon root 2, that is 39.58. I write it as 39.58 upon root 2. And if you calculate this, it comes out to be approximately equal to 27.99 volt, or I say approximately this is equal to 28 volt. I hope that this numerical is clear to you, that how to find this input voltage which is asked. Since no transformer is given here, had it been like this, that if I apply a transformer of 10:1, it's a homework for you. Okay, suppose I apply a transformer here of value 10:1. So what is the voltage at this side? Of course 10 times of this time, this much. It will be 280 volt on this side. Suppose I say that there is a transformer of 10:1, although it is not asked in the problem. So for the time being, I stop this half wave rectifier at this point, and I'll start with a full wave rectifier, and rather I'll start with a center tap full wave rectifier. So let me give first idea about this center tap full wave rectifier. While dealing with rectifiers, I told you the classification that rectifiers are divided into two categories. Rectifiers, I did this with you. Rectifiers are classified as half wave rectifier and full wave rectifier. Then further, this full wave rectifier, I told you it is center tap full wave rectifier, and of course another type of full wave rectifier, which is called a bridge rectifier. So I'll start with this center tap full wave rectifier. I'll start with this center tap I'm writing as FWR, that stands for full wave rectifier. What do you mean by center tap full wave rectifier? Initially, just let's see the circuit of this center tap full wave rectifier. It uses a transformer first of all, where an AC signal is provided, either a step up or a step down transformer. This is the inductive core here, represented by these two lines, vertical lines, and then I am using two diodes here. I'll explain this circuit later on. And this is a center tap transformer here, and here I use a load resistance RL. This is the load resistance RL, and the point is that the secondary of this transformer is grounded at the center. So this transformer, in case of half wave rectifier, we use a simple transformer like this. Simply. Now this transformer, if you see, these have three terminals, A, B, and this terminal C is also there. It has total 3 leads. This lead, this lead, and this lead. This transformer is called a center tap transformer. Center tap transformer. Now before coming to exactly into this, the working of this center tap full wave rectifier, because this rectifier is using, this circuit is using a center tap transformer, so it is called a center tap full wave rectifier. How it rectifies fully, that I'll discuss later on, but the point here is about this center tap transformer here. What do you mean by the center tap transformer? Now just see, an ordinary when I talk about a simple transformer, I'll talk about a simple transformer. What is if I take a simple transformer, the simple transformer is something like this, that you have an inductive core here. One side take some copper windings here, and on the other side you take some windings here, and this is called the primary and this is called a secondary. You apply, suppose you are using N1 number of turns are here, and here you have N2 number of turns. If the applied voltage is V1 and this voltage which you apply at this point is suppose V2, and I know that, and suppose I say that the current in a transformer, suppose I say that this current is I1 and this current is I2. So I know that V1 upon V2 is equal to N1 upon N2 is equal to I2 upon I1. This is general relation that you have already done in your previous classes. This is an ordinary transformer, simple transformer. Based on these turns, if N2 is greater than N1 or N1 is greater than N2, based on this you can say the transformer is either a step up transformer or a step down transformer. The working principle of a center tap transformer is also the same. It is same. Now when I talk about a center tap transformer, it is a similar kind of transformer, you can say, same type of transformer. You have an inductive core here, some windings on this side, and some number of turns on this side. But the point is that suppose that I have made 500 turns here. Suppose I say that the value of N2 is 500. There has been 500 turns like this. I take a copper wire and I make some turns on it. Suppose there are 500 turns. So what I do, wherever I obtain exact 250 turns, I ground that point. You simply ground that point. I simply ground it here at the center point, at zero potential. So this type of transformer is called a center tap transformer. Now what will happen? What happens in this? That suppose I have applied, suppose I applied 200 volt here. I apply 200 volt here, and suppose I say that the turns ratio of this transformer is 10:1. Let's take the same case here also. Suppose it is 200 volt applied here and the turns ratio is 10:1 in this case also. Of course, the voltage that you will obtain here will be 20 volt. It is a step down, 10:1. For simplicity I have taken 10:1. This V2 will be N2 upon N1 into V1 from here. This V2 you will obtain. Similarly, the potential between this point and this point, if it is 200 volt and this is 10:1, the voltage that you will apply between this terminal A and B will of course be 20 volt. Now the speciality of this transformer is that this 20 volt is divided equally into two parts. That here you will have, suppose I say this is point A, this is point and this is point C. This 20 volt is divided into 10 volt on this side and 10 volt on this side. That is the potential between A and C. If I apply a voltmeter between this point and this point, it will provide me, if I provide a voltmeter between A and B, of course it will be 20 volt. But when it is applied between this point and this point, it is 10 volt, and when voltmeter is applied between B and C, again it will be providing me 10 volt. This type of transformer is called a center tap transformer. So the point is that, again I am coming back to this circuit. This is a center tap transformer. This is supply voltage. So whatever voltage I get between A and B after being either step up or step down, the potential between A and C or between A and B will be half of the potential between A and B. Suppose it is 100 volt between A and B, so it is 50-50 on these two sides. So first thing is that. Secondly, there are two diodes. I hope that this center tap transformer is clear to you. Suppose there is two diodes D1 and D2. There are two diodes which are used in this type of circuit, that is D1 and D2. Now, theoretically, we'll assumption while dealing with this center tap transformer will based on certain assumptions, which does not happen practically, but theoretically we assume that very first thing, that the center tap is perfect. We assume that ideal center tap. Ideal center tap. What does it mean, ideal center tap? As I said in this example here, that suppose I say that there are 500 turns and you tap it. You simply tap it at its center at 250. But practically this does not happen exactly. Or what I say, that this 20 volt is divided into 10 volt and 10 volt exact. Ideally, practically there is a possibility that here you have 12 volt and here you have 8 volt. So very first thing is that we assume that this is an exact ideal center tap or exact center tap, that whatever voltage I obtain between A and B, I assume that this is an exact center tapping, and the voltage between A and C or B and C is exact half of the voltage between A and B. Very first thing is that. First assumption is that while analyzing this circuit. And the second assumption that I'll assume, there are two diodes, D1 and D2. In the very beginning I told you that we are not assuming any barrier potential, ideal one. But if this diode is having forward resistance RF, this is also having the forward resistance RF. Although practically this does not happen. The diodes taken out from the same box, made from the same factory at the same time, does not offer the same resistance practically. But theoretically we assume that these two diodes, if this is offering suppose 25 ohm, then we assume that this is also offering 25 ohm only. That is, we assume that the diodes are identical. Diodes are identical. So these are the two basic assumptions. On the basis of these two assumptions, first, that this transformer, center tap transformer, is having ideal center tap, means this voltage across the secondary is equally divided into two halves, and secondly, the diodes are identical, that is they are offering equal forward resistance. So based on these assumptions, in the next lecture I'll start with the working of this center tap full wave rectifier. So thanks for the time being.